So as it turns out, if you have a really short transmission line, it's okay if you have impedance discontinuities. And here's why. Let's imagine you have a transmission line and it's actually, I'll just draw it as one line. You know that there's like a forward and return conductor. And so we'll assume that there's some impedance here. Maybe this is the source impedance. And another impedance here. Maybe this is just the termination impedance. And so what happens is, let's look at the actual wave you're launching onto here. What is the wave that you're launching onto here? Well, initially, everything here starts out as 0 volts. So 0, 0, 0, 0, 0, 0. At every point along the transmission line, it's just 0 volts. Then all of a sudden, you launch a wave of 1 volt into the transmission line. So here it becomes 1. Then that wave propagates. Here it becomes 1. Here is 1. And that's how the 1 volt sort of wave would propagate. And I'm just making 1 as just a random number, just to illustrate. And so what it would actually look like is you have sort of a rising edge. If you were to look at the graph of the square wave over time, if you have like a square wave, it looks something like this. But this is actually kind of an idealized drawing. What it would actually look like are the sides would be slanted by a certain amount. And I'm kind of over exaggerating slanting here, but you would see a certain period of time required for the signal to rise to its maximum value, and a certain amount of time for it to fall as well. So you have this rise time and this fall time. So when you actually look at the wave that's propagating, it takes a certain amount of time for it to rise from 0 to 1. And so that correlates to an actual distance on the PCB. So over this distance, the wave is increasing. And then at the at the beginning of this distance, like let me draw it like this, like at this point you're at 0. Then during this distance, it's increasing. Then here it's at its maximum value. And then this whole wave just moves down the transmission line. So let's think about what happens if this transmission line is really short. And to start off with that, we need to look at what happens when the wave has reached the end of the transmission line. So let's reach the end here. Once this rising edge reaches the impedance discontinuity, so now you actually see a changing voltage here. Once this rising edge sees the impedance discontinuity, you see the reflected wave propagating backwards and adding to this rising edge. Let me get rid of this. Then that reflected wave is going to bounce back from the source, and it's going to have the opposite polarity. So as we've been saying, let's say this is 1 volt. Here you have 1 volt going back, and here you'll have, I don't know, some thing, well, it doesn't have to be 1 volt, just some positive voltage in this case, and then some negative voltage that's going to be reflected back. If this transmission line is like really short, like these two are like pretty close to each other, and I'll just label these as Z1, Z2, Z1, Z2. Then as it turns out, these reflected waves happen so rapidly, they traverse the transmission line so quickly that they actually sort of cancel each other out. What you see is sort of a damping of the ringing. Whereas you once had ringing that looked like this, now you'll see ringing that looks like this, or like something like that. Because these reflected waves from the source and the determination, they'll have opposite polarities, and so fundamentally this wave reaches here so quickly that it's able to sort of dampen the effect of this wave. And so that's kind of one advantage of having really short traces, is you can sort of get away with these impedance discontinuities because it's just so short. And there's multiple ways you can define how short a trace needs to be. Some terms we need to talk about. So we've talked about the rise time of a trace, or trace of a signal. We've talked about the rise time, and that's just sort of, let me draw it better. Okay. So that's just sort of, you have the square wave. How long does it take to go from 0 to its full value? Or actually the way that you usually define the rise time, you would see where is it at 10% of its value and where is it at 90% of its value. And so that's called the 1090 rise time. So it's going to be the 1090 rise time. You could also say the 2080 rise time, which is you start at your 20% mark and you reach your 80% mark. And so that's another metric. But fundamentally, you just have the rise time. You also have on your trace a certain propagation delay. So in the transmission line, and I guess I'm drawing both conductors here because, I don't know, I am. It takes a certain amount of time for the wave to cross this entire length, and that's called the propagation delay. So if we know that short traces are better, and then short propagation delays are better, then that suggests that there would be some relationship between propagation delay and rise time that will tell us how short does a trace have to be in order for it to, in order for you to have these repeated reflections, this whole phenomenon. So that relationship is essentially just the propagation delay has to be less than a certain factor times the rise time. There's a textbook by Craig Missner, which is really great, and it says this factor should be 1/2. There's a textbook by Eric Bogatin, which is also really great, and it says this factor should be 1/5. These are all just sort of rules of thumb, but essentially it just has to be small compared to the rise time. Because if you were to go back to this, it's only generating this reflected wave during the time that the signal is actually rising. After this whole signal has passed, after it's all the way up here, and you can imagine the rising edge is somewhere off here in imaginary distance, I guess. At that point, it's no longer generating a reflected wave because it's just sort of constant. These re-reflections might generate reflected waves, but the original incident wave is not doing that anymore. And so it's only during the rise time that you really care about as the rising edge. This would be called the rising edge. As the rising edge is incident upon the impedance discontinuity, you're generating these reflections. And so that's why if we can say if the propagation delay shorter than in this case like 1/5 of the rise time, we can say the trace is sufficiently short that these re-reflections, this term, the propagation delay, it tells you how quickly do these reflections bounce around, rattle around within the transmission line, because it's the time it takes for the wave to traverse the transmission line. And so the propagation delay is really small relative to the rise time, literally on the rising edge of the signal. So let's say this is the rising edge. I'll just draw it out here. So you have a reflection here, but then it's going to be canceled out by another reflection that came later, then a reflection here, but then a reflection here. So they're sort of, I've literally seen a textbook say that they're smeared out over the rising edge. So that's kind of the reasoning behind this formulation of propagation delay less than 1/5 the trace, the rise time. There's another way you can sort of quantify this, and this is in terms of distances. Because if you, I'll just redraw this whole thing. If you were to take this transmission line and you were to look at the rising edge, it takes a certain, this is a certain distance, a physical distance on the transmission line. At this point on the transmission line is 0. At this point on the transmission line is 1. In between, there's a certain distance, and that's, we're going to call it the spatial extent of the rising edge, or LSE. And so that we can imagine the length of the entire transmission line. Again, if we know the length of the transmission line has to be short, and I'm just going to call this L, we can say that there's some relationship, some inequality. L is less than, again, some factor times LSE. So the length of the transmission line has to be short. And again, this could be 1/2 or 1/5 or whatever. A really nice rule of thumb is when you have the length of the transmission line in inches, if you can say that it's less than the rise time in nanoseconds, and this is just the numerical values. You can't compare inches and nanoseconds, but just take the actual numbers. If you can say that the length in inches is less than the rise time in nanoseconds, then it is short enough. And this is a rule of thumb, literally just based on how the units work out and how the unit conversions sort of just lead to like formulas like this when you just work out the numbers. But this is a really useful rule of thumb. If the length of the transmission line in inches is less than the rise time of the signal in nanoseconds, you can reasonably say you don't have to worry about impedance, about this ringing from impedance discontinuities.